All right, let's talk now about Cournot competition. So Cournot duopoly or quantity competition. In this scenario, you have only two firms. They have some market power, but not entire market power as a monopoly. And they are going to compete by quantities. Each firm will choose a given quantity in this game. Okay, that's their action. So you have two players, set of players has firm 1 and firm 2. They are facing an inverse demand P equal 1 minus Q. Q is the aggregate quantity, is the sum of whatever firm 1 produces plus whatever firm 2 produces. Little q is the action of firm 1, it's what it's firm 1 produces, Q1, and Q2 is how many units firm 2 produces. Okay, we have a homogeneous, perfectly divisible good, Q is the aggregate quantity. Simultaneous moves game, the firms choose their quantity without knowing how many units the other firm will produce. Quantities can be fractions, but they cannot be negatives. We assume firms have zero cost to make it easier. You can put a game Cournot with cost as well, there's no problem, just to make the calculations easier. And the payoff, the goal of the firm is to maximize their profit. The profit of firm J is price times quantities. In this case, profit is equal to revenue because the total cost is zero. Okay, so profit of firm 1 is the price. The price is 1 minus capital Q. Capital Q is Q1 and Q plus Q2, right? Aggregate quantity. So this is the price times the quantity that firm 1 is producing. Profit of firm 2, 1 minus the price minus the quantity, the aggregated quantity. The sum here is the aggregated quantity, so this 1 minus the aggregated quantity is the price times the how many units firm 2 is producing. Okay, now I'm plotting here on the vertical the profit of firm 1 as a function of the quantity firm 1 is producing for assuming some fixed Q2. Okay, so that's a parabola. It's a polynomial of degree 2. If you think of Q2 as a constant, this is a concave parabola. If you play Q1 equals 0, this whole thing is 0. We are at this point here. But the parabola is like that. Right? If you play Q1 equals 1 minus Q2, we are also at 0. And if you play more than that, you have negative profit. If you play strictly between 0 and 1 minus Q2, you have some positive profit. A parabola, the vertex of the parabola is right in the middle. It's the symmetric point, is in the middle between 0 and 1 minus Q2, right? So that's what player 1 will do. What firm 1 will do is to maximize its profit, choose the vertex of the parabola, and therefore the best reply of firm 1, best reply against any action of firm 2, it's going to be 1 minus Q2 over 2. Why? Because it's the middle point between 1 minus Q2 and 0. How do I know this is 1 minus Q2? Well, if I plug here 1 minus Q2 instead of Q1, this is going to be 0. Okay, in the graph it's easy to see. Okay, however, that is if Q2 is smaller than 1. If Q2 is bigger than 1, this would be negative. I cannot do that. Right? What is the problem? Well, if your opponent is inundating the market, the price is already 0, so you would not want to participate. There's no space more for you to produce some positive quantity and have positive profit. So you might as well not play or play 0, right? In that case. And for your opponent, for firm 2, the best reply of firm 2 against an action of firm 1, you also have to break into two things. We are going to search for Nash equilibrium with these properties where the two firms are playing positive but smaller than 1 quantities. Okay? So let Q1 star and Q2 star be a candidate Nash equilibrium. Okay, a profile of actions that it will be a Nash equilibrium. That means that Q1 star is the best reply of Q1 against Q2 star. So player 1 is playing a best reply against player 2. And player 2 is also playing a best reply against player 1. Okay, so pick a pair of quantities with this property. It's a Nash equilibrium. Okay, we are calculating Nash equilibrium. The stars means it's a Nash equilibrium, and each player is playing a best reply. So if Q1 star equals to that, 2 times Q1 star is 1 minus Q2 star. 2Q1 star is 1 minus Q2 star, and 2Q2 star is 1 minus Q1. Now we have a simple system, 2 linear equations, 2 variables. Even I can do this, but, and we can go on and calculate Q1 star and Q2 star, okay? The solution will be here. Q1 star and Q2 star are both 1/3. In terms of picture here, I'm doing a nice picture. In this axis I have Q1, in this other axis I have Q2, and I'm plotting the best replies. Okay, so here in blue, the best reply of player 1, according to this specification here. So if player 2 is playing Q2 is 0, player 1 should play 1/2. If Q2 is 0, player 1 should play 1/2. And then as Q2 increases, Q1 goes down all the way to when Q2 equals 1, this is 0, is this point here. Okay? Goes down linearly, so this is the best reply of player 1. The same thing we do for player 2. If player 2 is facing a player 1 who plays 0, player 2 should play 1/2. So if Q1 is 0, player 2 should play 1/2. And then the production of Q2 goes down as the production of Q1 increases. The more your opponent plays, the less you want to play. You want to produce, okay? With this slope 1/2. And the intersection point here is 1/3 and 1/3. That's the Nash equilibrium of the game. So, in conclusion, that's the outcome of the game. Both firms play 1/3 quantity. The total aggregate quantity is this plus that, 2/3. The price will be 1/3. And if I draw the inverse demand here, the aggregate market price as a function of aggregate quantity, this Cournot point is here at quantity 2/3 and price 1/3. The monopoly would be here, right? And the perfect competition would be here. Zero marginal cost, because there are 0 costs, right? So basically every firm sells for free the product, 0 price. And so yeah, the Cournot is somewhere between the monopoly and the perfect competition. Firms have a little bit of market power, there's a little bit of deadweight loss, but not that much. Okay? In the monopoly, the deadweight loss would be the area of this triangle here. In the Cournot, it would be just the area of this triangle here, the deadweight loss. And in perfect competition, there's no deadweight loss, it's efficient. Okay? So that's the beautiful story of Cournot. Cournot did this kind of work in 1839, so a long time ago. Very clever guy, huh? Augustin Cournot. See you guys next time. Bye bye.